Thanks for joining me as we do our Unit 2 target check. So we're going to start right off the bat with target 1, just talking about if we have a function or not. So graphically on A through D, what we're looking for is if our graph passes the vertical line test, meaning if I scanned a vertical line across it, it would not touch more than one point at a time. So this would be a function. This passes the vertical line test. This is a function that's actually a linear function. On C, right there, it does not pass the vertical line test, so this is not a function. And then on D, it passes, or it doesn't pass a lot of places. There's one example of a place, so that would be not a function. If you look on E, when we think about a table or even a set of points, if each input has exactly one output, so each input has its own output. 0 always has an output of 5. It's not like it has an output of 5 and 6, it's always 5. So this is an example of a function even though the outputs are all the same. That's okay. And then on F, you should be able to identify that as a quadratic. And we know that quadratics are functions. We always use the phrase quadratic function. Moving on to target 2 when we're evaluating. So we have a series of tables, graphs, equations, all representing functions, and we have to evaluate them at different points. So we take this input value, -4, and we look at this specific function. So I'm looking for the M function, which is this piecewise equation. So for a piecewise equation, I look at the inequalities, and I see where our input value of -4 makes a true statement. -4 is less than -3, so I'm going to plug in a -4 to this top equation. So that would give me -20 plus 3, which is -17. Same idea here on B, we're doing h of 2. So I'm going to go to the h function, which is that first graph, and the input value is 2. So if you look at where the input value is 2, where x is 2, it's along that line. It intersects with our function right there. And remember, our answer is always the output. So the output at that point is 1. The y value is 1. On C, g of -3, I'm looking for the g function. It's that first equation, and I'm going to plug in a -3 for x. So that would give me -3 squared is 9, times 3 is 27, plus 5 is 32. K of -1. So for k of -1, I'm looking at the table. When the input is -1, the output is 3. For j of 1, I'm looking at the j function, which is the piecewise graph, the second graph. Where the input is 1, I can actually see there's 2 points. One has an open point, one has a closed point. Remember, for piecewise functions, we always pick the closed point. The output of that closed point is 1. And then we have m of 0, so we're going to take the 0 to the m function, which is this piecewise function. And again, we're going to take a look here. Where would 0 make a true statement? It would make a true statement in the second equation, or the second inequality. 0 is greater than -3. So I'm going to plug it into the second equation. 1/3 times 0 is 0, plus 1 is 1. Moving on to the second page, we're identifying our functions as linear, absolute value, or quadratic. So this first one is a V shape, so that would be absolute value. The second one is a line, which means it's a linear function. The third one, this is in y equals mx plus b form, which is how we write our linear functions. And then here we have an absolute value. So that's going to be an absolute value function. I know it has x squared, but the fact that we have absolute value brackets means that it's absolute value. All right, so then we're going to look at our table, and remember we look for the rate of change. So from 5 to 0, we go down 5, down 5. So it's down 5 all the way through, so that would be a linear function. Here, if we look at the rates of change, that would be down 1, and then it would be up 1. So this looks like an absolute value right now, but then it goes up 3. So the non-constant rate of change means this is a quadratic. Target 4 is solving absolute value equations. So I'm first going to work to get the absolute value brackets by themselves. So I'm going to add 3 over. So I get the absolute value of x over 2 equals 2. And so I'm looking for if that would be like a no solution case, which it wouldn't because the absolute value could equal 2. So then I'm going to create two equations. X over 2 equals 2 and x over 2 equals negative 2. And I'm going to solve in both cases. So to get rid of that x over 2, that x divided by 2, the opposite would be multiplication. So I have x equals 2 times 2, which is 4. Or over here, if I multiply both sides by 2, I get x equals negative 4 as well. All right, let's take a look at B. I'm going to subtract 9 from both sides. So I'm working to get those absolute value brackets by themselves. That would be 5. And then I'm going to divide by 5. So again, at this step right here that I'm writing, we want to just pause for a second. If these absolute value brackets were equal to a negative, that would be a no solution situation. But because they're not negative, it's not equal to a negative, I'm going to make my two equations, and I'm going to solve both of them. This is not no solution. So in this first one, if I subtract 7, I get 6k equals negative 6. If I divide by 6, I get k equals negative 1. Over here, if I subtract by 7, I get 6k equals negative 8. And then if I divide by 6, I would get negative 8 over 6, which is negative 4 thirds. If you wanted to use the rounded value there, the decimal, that's fine. So sticking with our absolute value, now we have absolute value inequalities. So here I treat them in a very similar way that I would an equation. So on A, I'm going to divide both sides by negative 5. Here, I'll rewrite it so you can see. So I'm going to divide both sides by negative 5 to get the absolute value brackets by themselves. But what you have to remember is when we divide by a negative, we have to switch the sign. And then we have negative 45 divided by negative 5, which would be positive 9. And then I'm going to treat this like I did the equations. So I'm going to put x plus 9 equal to 9 and x plus 9 equal to negative 9. And I'm going to solve in both cases. So if I subtract 9 over here, I get 0. If I subtract 9 over here, I get negative 18. And these are going to be what I call my key values. So going back to the inequality symbol, remember it did not have an equal to part to it. So at 0 and negative 18, I'm actually going to have open points. And then I'm going to use a test value. So I always like to use 0, but I can't here because it's actually one of my key values. So I'm going to use the value of 1 or 2. I'll use 2, which would be right there. So if I plug in 2 to this original problem, I would have 2 plus 9, which is 11. The absolute value of 11 is still 11. Times negative 5 would be negative 55, and negative 55 is not greater than negative 45. That would be a false statement. So this number out here at 2 made a false statement, so I'm going to shade in between these points, and you could even test a value in there. For your final answer, since it's in between, it would be everything between negative 18 and 0. And then on the second one, On the second one, we're going to get those absolute value brackets by themselves again. Do you want me to do it? You want me to bring them down tomorrow, or do you want to switch them now? Okay. Sorry. On the second one, we're going to get those absolute value brackets by themselves. I still need a grade there. Reflection. Okay, so I'll keep these. On the second one, I'm going to add 8 over first. I'm going to rewrite the problem. And then I'm going to divide by 3. So I get the absolute value of negative 10 minus 9n is greater than, as I'm dividing this in my calculator, remember that you also have some special cases with inequalities, so that's 26. So if you had a negative number, let's say that's a negative 26, if you had the absolute value is greater than negative 26, that would always be true. But if you had the absolute value is less than negative 26, that can't ever be true because a positive would never be less than a negative. It's just not a special case here, but I just want to remind you that we do have those special cases you want to look out for on your test. So I'm setting it equal to a positive 26 and a negative 26, just like I've been doing. And I'm going to solve both of these. I'm running out of room here, so I'm going to not show all of my work here. But I got negative 4 for this key value. And over here, that would give me a negative 16. And then if I divide, that would be 16 ninths. And again, if you wanted to go ahead and round that, you could, especially because we're going to have to put this on a number line. So that gives me 1.8. So those are key values, negative 4, 1.8. Just like before, those are open points because we don't have an equal to in our inequality symbol. I'm going to test the value of 0. I can do that this time because 0 wasn't my key value. And if I plug in a 0, I would get 22 is greater than 70, which is a false statement. That means we shade on the outside. So when I plug that in, I'm just going back to that original inequality and seeing if it's a true or false statement. If I wanted to write my answer here, I'd have to break it up into an OR statement. So either n is less than negative 4 or n is greater than 1.8. Moving on to target 6 and 7, we're going to find their M, H, and V. Thank you. Sorry. So starting with A, M is that value out in front. It's negative 1/4. H is going to be the opposite of what's in absolute value brackets at negative 3. And VE is going to be what's at the end. So the vertex is at negative 3, 1. That's the very first point that you should make. So negative 3, 1. And then we're going to use our slope of negative 1/4. So down 1 over 4 in both directions. I actually can't fit another one on that one way. And here is our absolute value graph. Domain, how far to the left and right? It goes forever to the left, forever to the right, all real numbers. The range, this opens downward, so we're going to say y is less than or equal to, and look at the y value of your vertex. It's at 1. The x-intercepts we can see on our graph, they are at negative 7, 0. Notice how I'm writing this as a point, and also 1, 0. Now for the y-intercept here, I actually can't tell exactly where it's crossing. So remember, you can find this algebraically. So if I want to find the y-intercept algebraically, I would plug in a 0 for x. And then I'm just going to solve this. So that would be negative 1/4. 0 plus 3 is just 3. The absolute value of 3 is 3. So this would be negative 3/4 plus 1, which would ultimately be 1/4. So the y-intercept is at 0, 1/4. And you guys can just throw that in your calculator. You don't need to show all that work. All right, same thing here on B, just new numbers. So M is 3, H is 1. Remember, it's the opposite. V is 5. So we have a vertex at 1, 5. Go ahead and plot that, and then we use our slope of 3 to graph the rest. So up 3 over 1. This is a really thin absolute value. Domain should be all real numbers, goes forever to the left, forever to the right. This one opens upwards, so we're going to say y is greater than or equal to the y value of the vertex is 5. X-intercepts, it's never going to cross the x-axis, so I'm going to write none. And the y-intercept, make sure you're paying attention to your point. My line there was kind of wonky. So it would actually cross at 0, 8, even though I have it drawn a little bit off of that line, or off of that point. Moving on to the next page, we get into writing equations of quadratics. So we're just going to work backwards. So remember our equation that we were just dealing with. We're going to fill this in working backwards. So I'm going to look where the vertex is. The vertex here is at 3, -2. That means H is 3 and V is -2. And then I can determine what the slope is. It looks like we're going up 2 over 1. So the slope is 2. So I'm going to fill all this into that equation I wrote up at the middle top. Y equals slope is 2. Switch the H, so it's x minus 3 and then V. Same thing over here. Here's your vertex. That vertex is at -2, 3. So H is -2, V is 3. The slope looks like we're going down 1 over 1, so that would be -1. So our equation is y equals negative, and you could put a -1, but I'm just going to put a negative symbol. The opposite of x, or sorry, the opposite of h, so x plus 2, and then v minus 3. So now we're going to do those same 3 steps, but now we're going to do it with a quadratic. And so there's lots of ways to do this. I think the majority of my students have used the pattern of 1, 3, 5, 7. So I'll continue to reference that again and again here. So taking a look at our first example, we have m is 2, h is -1, so it's the opposite of what's in parentheses. It's very similar to absolute value, and v is 3. So that means our vertex is at -1, 3. Okay, so this doesn't have a constant slope, so we can't just go up 2 over 1, up 2 over 1, and continue that pattern here. So instead what we're going to do is take our m value, which is 2, and we're going to multiply all of these numbers by 2. And that's our new pattern. So I'm going to go up 2 over 1. But if you notice, the next step says 6, so I'm going to go up 6, which actually takes me off the graph, over 1. And that's how I would work with that pattern. So the non-constant rate of change follows the 1, 3, 5, 7 pattern. Your domain of absolute value is still all real numbers. The range works the same way that we did with the absolute value. So the y value of this is 3, and it goes above that. So y is greater than or equal to 3. X-intercepts, it doesn't cross the x-axis. And the y-intercept we can see at 5. So same idea over here on B, just new numbers. So m is -1, h is +3, and v is +5. So our vertex is at 3, 5. 3, 5. All right, so in this case, m is -1. So I'm going to take that 1, 3, 5, 7 pattern, and I'm going to multiply it by -1. And all that means is you're going down. So we're going to go down 1 over 1, down 3 over 1, and then down 5 over 1. You could continue that pattern if you wanted to. So domain, it's still going to keep going to the left and right, getting wider and wider, all real numbers. The y value of the vertex is at 5, and it goes below that since it opens down. Y-intercept, I can see I have a point at 0, -4. If you needed to solve for your y-intercept, remember you can always plug in 0 for x. I didn't ask for the x-intercepts here because we can't see them clearly. We could guess where they are, but we don't want to guess. And now we're just going to move backwards from that. So this time we're going to write the equation of our quadratic function. So I'm going to start with the vertex, -3, -4, which means h is -3, v is -4. And that 1, 3, 5, 7 pattern, remember that. Let's see if we can figure out what that, if it follows 1, 3, 5, 7, or maybe a multiple of that. So it looks like the next point here is right here and here. So that means we would have to go up 4, which means we multiplied by 4. So this next one would be 12. So we can kind of test that theory because you can see that this, like, it doesn't cross, there's not another clear point up here or up here. So I think we're pretty safe to say that the slope is going to be 4. So filling in our equation, it would be y equals slope, parenthesis, change your x, or change your h, don't forget the squared, -4. Over here on B, I'm going to show you what you can do if you're really not certain what that slope is, because on this one, it's really hard to tell. So like here's our vertex. So we for sure know that our vertex is at 6, 8. So we for sure know that h is 6 and v is 8. But beyond that, it's really hard to tell what the pattern is. So we can actually use our equation and fill in what we do know. We do know h and we do know v. So h is 6, so I'm changing the sign there, so it's -6, plus 8. And if you look, this problem actually gives us another point at 1, 3. 1 represents an x value, 3 represents a y value, so we can go ahead and plug those into our equation as well. So if I simplify this, inside the parentheses, 1 minus 6 is -5. -5 squared is 25. Then I'm just solving this equation, so I'm going to subtract 8, so I get a -5 equals 25m. And if I divide by 25 and simplify, I get m equals -1/5. I would have not been able to tell that just based on observing like I did on A. So I'm really glad that I solved for that. And now I'm just filling in all of my information. And that method of solving, it would have worked on A as well. It's just that I didn't need to, so I wanted to take that shortcut when it was available to me. All right, so in Target 12, we're graphing piecewise functions. I like to do this from tables. So I make a table for each line in the equation. So I have 2x plus 3, x is less than -2. So here's my table for that part. I'm going to start it at -2 since it's the number in the inequality. And it says x is less than -2, so I'm going to choose some numbers that are less than -2. Then I'm going to plug them into the equation and see what I get out. So on this first one, I would get out a -1. That would be -6 plus 3, which is -3. That would be -8 plus 3, which is -5. And before I plot these points, the last thing I'm going to think about is the fact this will be an open point since it is not equal to. So -2, -1 is an open point. That's off a little bit. I'll redraw it. And then -3, -3, and -4, -5. And then I'm going to do the same thing just for the second equation. So 1/2 x minus 2 x is greater than or equal to -2. And I'm going to make a table. I'm going to start the table at -2 because that's the number in the inequality. And then I'm going to choose some numbers that are bigger than -2 and plug all of those into my equation here. So 1/2 of -2 is -1, minus 2 is -3. If I plug in a -1, that would give me -2.5. This gives me -2. That gives me -1.5. And before I plot that first point, since it is equal to, x is greater than or equal to -2, it is a closed point to start with. So -2, -3, and then I have -1, -2.5, -2, -1.5, so working its way up like that. And this passes the vertical line test, which is a pretty good indication that I've done it correctly, since all of piecewise functions should pass the vertical line test. Moving on to B, it's going to be the same idea, it's just there's 3 parts to it. So starting off with the first part, x plus 2, x is less than 0. So I'm going to choose 0, since that's the number in the inequality, and then a couple numbers less than to follow the inequality. If I plug in a 0, I get out a 2. If I plug in a -1, I get out a 1, and then I get out a 0. Since there's no equal to, this is going to be an open point. So 0, 2 is an open point. -1, 1. I'm going to redraw that first one. -1, 1, -2, 0. Starts at the first point, goes through the next few. Taking a look at the second line, 1, 0 is less than or equal to x is less than or equal to 3. So I have an xy table, and I'm going to choose the 2 numbers that are in the inequality. So I'm just going to use 0 and 3. I know it looks kind of crazy, but it actually makes it easier. It just tells you which numbers to choose. If I plug in a 0 or I plug in a 3, it's kind of weird because it's just a 1, so there's no x, which means we just always get out 1. And if you look at the inequality, both of these should be closed points. So 0, 1 is a closed point, and that just sits right below. Kind of hard with my smartboard marker. And then 3, 1, and we just connect. So remember, when your inequality is written like that, it means it's a segment. It starts at one point and goes to the next point. I'm going to make the last table over here, so x plus 4 and x is greater than 3. Now I'm recording. So since there's a 3 in the inequality, I'm going to use 3 first. And then I picked 4 and 5 because those values are greater than 3, so x is greater than 3. If I plug in a 3, I get out a 7. If I plug in a 4, I get out an 8. If I plug in a 5, I get out a 9. And then again, just think about if your first point is open or closed, and this one is open. So 3, 7 is our first point. Then 4, 8. And then 5, 9. Start at your first point, go through your next 2. It should pass the vertical line test because it is a function. All right, our last 2 targets, they get paired up here. So we're writing the equation of a piecewise function. Starting with A. So we have 2 parts here. Doesn't matter the order in which you number those, 1 or 2, or even if you number them. We're going to write the equation of line. So we need to know 2 pieces of information. We need to know what slope is, and we need to know what the y-intercept is. So on this first part, the slope is down 1 over 5, so it's -1/5. We can look at the graph and see that the y-intercept is 8. So the equation of that line is -1/5 x plus 8. For this one down here, it's a horizontal line, which means the slope is 0. If you continued this line, you could see it would cross the y-axis at -4. So the equation would be 0x minus 4, or just -4. For the inequality part, look at for your break in your graph. The break in the graph is happening at 5. So we're going to start our inequality with x, and it's going to end with 5. We just have to decide on the inequality symbol. So this first part of the graph is to the left of the line. It's going that way, which means it's less than. It's going to be equal to because it starts with a closed point. For the second part, it's going to the right, which means it's greater than, and I'm going to leave off the equal to because it's an open point. Your domain talks about how far to the left and right your graph is going. It should be all real numbers, so you can always check that whenever you're actually creating the graph. And then for your range, we're going to break this up into 2 parts. So for this first part, it's just a horizontal line at -4. It never goes above or below -4. For the second part, it starts at the y value of 7 and goes up from there. Remember, it had a close point, so that's why I did an equal to for that one. And then on the second one, it's the same thing, just different numbers, different graph. So for this first part, what I've labeled as the first part, the slope would be -1/3. It's going down 1/3. The y-intercept, I could predict if I continue that slope, it's going to cross at 1. So my first equation is -1/3 x plus 1. And for the second part up here, that slope is down 2/3, and the y-intercept we can see is at 5. So the second equation is -2/3 x plus 5. And then we have our inequalities. So the break in the graph here is at 3. So I'm going to start my inequalities with x. I'm going to end at 3. Part 1 went to the right of the graph, so I'm going to say greater than, and it started with a closed point, so it's equal to. Part 2 went to the left of the graph, so I'm going to say less than, and it started with an open point, so it's not going to be equal to. For your last domain and range, it's going forever to the left and right, all real numbers for domain. For the range, we're going to break it up into parts. So starting for this first point, or first part, it starts at the y value of 0 and goes down. So y is less than 0. It is also equal to, that's a closed point. Or this one starts at the y value of 3 and goes up from there. I'm not going to include an equal to because it is an open point. And that is your test review.